welcome you all. In the last few lectures, we have seen that how to find out the solution of ordinary differential equations using Laplace transform, where we have considered the ordinary differential equations with constant coefficients, with variable coefficients, and also the solution of simultaneous linear ordinary differential equations. So, these things we have discussed in the last topics of Laplace transform. Now, we will see the what is integral equation and the solution of integral equations and the use of Laplace transform of this in the solution process of this integral equation. An integral equation basically an equation which says that where the function f which we have to determine should come under integration sign. Basic idea is this one. This is an equation involving some variables, some functions, where one function value I have to determine and that function should come under the sign of integration and it should be there in the other places also. You see the form of an integral equation f t equals y t plus a to b k u t f u d u. This is an integral equation where the function f t we have to determine, and if you see your f t is coming under the integral sign also. So, please note this one that f t equals y t plus a to b k u t f u d u. This is known as an integral equation where your y t is a known function, k u t basically is the kernel of the integral equation, a and b are given constants or it may be the function of t also, it may be the function of t also, and f t is the function which we have to determine. So, please note that the function f t is coming inside the integral sign and then only we call it as an integral equation. Various kinds of integrals equation are available. One is freedom integral equation, it takes the form f t equals y t plus a to b k u t f u d u. Of course, it is almost similar where a and b are only constants. Please note that a and b are only constants, then we call it as freedom integral equation. There is another type which we call as Volterra integral equation. The form is similar f t equals y t plus a to b k u t f u d u, where the only difference with freedom is here a is constant and b equals t. Only difference is this one that a is a constant, b equals t. As I told you, a may be a constant, a and b may be constant or some function of t. So, in freedom integral equation a to b where a and b both are constants, in Volterra integral equation a is a constant whereas b equals t. That is another one which integral equation of convolution type, which takes the form of f t equals y t plus 0 to t k of t minus u into f u d u. If you remember, for the convolution type function should be f x into g of t minus x. So, here it is f t equals y t plus 0 to t k into t minus u into f u d u. There is another type which we call as integro differential equation. This integro differential equation is f dash t equals f t plus y t plus 0 to t sin of t minus u into f u d u. That is, it involves not only the function which we have to determine, but also the derivative of the function f dash and which takes the form f dash t equals f t plus y t plus 0 to t sin of t minus u into f u d u. This Abel's integral equation which is not visible properly, let us write down this thing. This Abel's integral equation, we may write down Abel's integral equation which takes the form of g t equals 0 to t f u into t minus u whole to the power n into du, where g t is known function, and your n belongs to 0 to 1. See, please note this one, that in Abel's integral formula g t equals 0 to t f u by t minus u whole to the power n into du, where g t is a known function and n belongs to 0, 1, and I have to find out the value of f u. So, I have given a few well known type of integral equations. Now, we will see using these integral equations and using Laplace transform how to find out the solution of these integral equations. First, take this form. I want to solve an equation like this. Solve f t equals 0 to t sin u cos of t minus u into du. I have to find out what is the value of the function f t. So, here if you see your f t I am writing, which I have to find out 0 to t sin u into cos of t minus u into du, and this is nothing but the from the definition of convolution. I can write it as sin t star cos t. From the definition of convolution, I can write down this is equal sin t star cos t, sin t convolution cos t. Now, I can take Laplace transform on both sides of the given equation. If I take the Laplace transform on both sides of the given equation, I will obtain Laplace transform of sin t convolution cos t. And from the property of the convolution, using the theorem, I can write it as Laplace transform of sin t into Laplace transform of cos t, which is known to us. So, once I know Laplace transform of sin t, Laplace transform of cos t, which I can write down like this 1 by s square plus 1 into s by s square plus 1, where 1 by s square plus 1 is the Laplace transform of sin t and s by s square plus 1 is the Laplace transform of cos t. So, that you can write down Laplace transform of f t, this is equals to s by s square plus 1 whole square. So, once I am getting Laplace transform of f t equals a function of s, that is s by s square plus 1, I can find out the value of f t using inverse Laplace transform, that is f t equals Laplace inverse s by s square plus 1 whole square. So, I can write down Laplace f t equals Laplace inverse of s by s square plus 1 whole square. So, in any case, either I have to find out the Laplace transform or I have to find out the inverse Laplace transform. So, this I can write down half into, I can make it as 2s, this is as 2s and this as half over here. So, this half will go out. So, 2s by s square plus 1 means this, using theorem I can write out dds of 1 by s square plus 1. Using the property of inverse Laplace transform, I can write it half into L inverse dds of 1 by s square plus 1, and this is equals to minus half into minus 1 into t to the power 1 into t into Laplace inverse of 1 by s square plus 1 from this dds, and this is nothing but this becomes t by 2 and Laplace inverse of 1 by s square plus 1 is equals to sin t. So, here after dds I am making the derivative of this one, and after that I am getting Laplace inverse of 1 by s square plus 1, whose value is t by 2 into sin t. Therefore, for that integral equation, the value of f t is equals to t by 2 into sin t. Let us see the quickly this one, f t equals sin t convolution cos t, Laplace transform of f t equals Laplace transform of sin t convolution cos t, and using the convolution theorem, this I can write down Laplace transform of sin t into cos t. This again Laplace transform of sin t is 1 by s square plus 1, whereas Laplace transform of cos t is s by s square plus 1. So, that I am getting Laplace transform of f t equals s by s square plus 1 whole square. And f t I can obtain Laplace inverse of this quantity, which using property I can write down minus half into Laplace inverse of ddS of 1 by s square plus 1. And if I take the ddS, I will obtain half into minus 1 t Laplace inverse 1 by s square plus 1, and Laplace inverse of 1 by s square plus 1 is nothing but sin t. Therefore, value of f t is equals to sin t. So, by this way, even if we have the integral equation using the convolution, using the properties of Laplace transform, I can find out the solution of this. Now, let us take some other type. We want to solve the equation f t equals 1 plus 0 to t f u into sin of t minus u du. Let us see the solution process. Your f t equals, it is given 1 plus 0 to t f u into sin of t minus u du, and this integral is nothing but convolution of two functions. One is f t, another one is sin of t. This is your f u, this is sin of t minus u. So, from the property of the integral, we can write it as f t convolution sin t. Now, take Laplace transform on both sides of the given equation. So, that this equals, you can write down Laplace transform of 1 plus Laplace transform of f t convolution sin t, and this Laplace transform of 1 is 1 by s plus this Laplace transform of f t convolution sin t I can write down from the theorem. Again Laplace transform of f t into Laplace transform of the function something like sin t. So, this is equals 1 by s plus Laplace transform of f t into Laplace transform of sin t is 1 by s square plus 1. So, this Laplace transform of f t into 1 by s square plus 1, I can take it on the left hand side of the equation, and I can take Laplace transform of f t as common. Then I will obtain 1 minus 1 by s square plus 1 into Laplace transform of f t. This is equals to 1 by s. So, that now I can write down Laplace transform of f t in terms of s only. So, in the next one we will can write down Laplace transform of f t. This is equals s square plus 1 by s cube. So, that you can find out now f t will be Laplace inverse of s square plus 1 by s cube. So, once I am getting this Laplace inverse of s cube plus 1 by this I can write down 1 by Laplace inverse of 1 by s plus 1 by s cube. This we can write down, and this is nothing but 1 by s is 1. For the function 1, Laplace transform is 1 by s. Similarly, for 1 by s cube, the corresponding function will become t square by 2. So, that the solution of the function, the value of the function f t is equals to 1 plus t square by 2, for which the integral equation will be satisfied. Let us see quickly here also. So, f t equals 1 plus f t star sin t. So, Laplace transform of f t we are writing in this format. Then we are writing Laplace transform of f t equals 1 by s plus Laplace transform of f t into Laplace transform of sin t. You are putting the value of Laplace transform of sin t equals 1 by s square. You are taking this Laplace transform of f t into 1 by s square plus 1 on the left hand side. So, that Laplace transform of f t into that term equals 1 by s, and in the next one I can write down Laplace transform of f t equals s square plus 1 by 1 by s cube, and from here I can write Laplace inverse f t equals Laplace inverse 1 by s plus 1 by s cube, and this I am breaking into two parts. and directly I can write down f t equals Laplace inverse of 1 by s is 1 and Laplace inverse of 1 by s cube is t square by 2. So, that the value of f t equals 1 plus t square by 2. Now, let us see the another problem involving the Bessel function. We want to find the value of 0 to t j 0 u j 0 t minus u into du. Suppose your f t is 0 to t j 0 u into j 0 t minus u du. We are starting from here. So, this is nothing but j 0 into j 0 u. So, if I take Laplace transform of f t, directly I am writing this, I can write down Laplace transform of j 0 t into Laplace transform of j 0 t. This using convolution I am writing it. This integral is nothing but j 0 t star convolution j 0 t. If I take the Laplace transform, I can break it into two parts. So, that this is equals 1 by root over s square plus 1 is the Laplace transform, here also 1 by root over s square plus 1. So, that you will obtain this value as 1 by s square plus 1. So, Laplace transform of f t is equals to 1 by s square plus 1 and f t, then I can write it as Laplace inverse of 1 by Laplace inverse of 1 by s square plus 1 and Laplace inverse of s square plus 1 is equals to sin t, which is actually the value of this f t. Therefore, value of this integral 0 to t j 0 u j 0 t minus u du is nothing but sin t. Using these convolution properties, very easily we are determining the value of this one. So, let us just see it once. If your f t is 0 to t j 0 u into j 0 t minus u du and then taking Laplace transform and using the properties of convolution, I can write down Laplace transform of f t equals Laplace transform of j 0 t into Laplace transform of j 0 t. So, Laplace transform of j 0 t, we know it 1 by s square plus 1. So, that Laplace transform of f t is 1 by s square plus 1. So, you will obtain f t equals Laplace inverse 1 by s square plus 1 and whose value is nothing but sin t. Let us see another example which involves the differential type. Basically, f dash is there, f is also there, both are there, f and its derivative are there and we have to find out the function f t. So, we want to solve the function f dash t equals sin t plus 0 to t f of t minus u into cos u du, provided f 0 is equals to 0, the condition is given over here. So, your f dash t equals sin t plus 0 to t f of t minus u into cos u du. So, as we have seen previously, this f dash t equals, we can write down sin t plus, this is nothing but the convolution of two functions f t and cos t. So, I can write it as f t convolution cos t. Now, take Laplace transform on both sides of the given equation. If you take Laplace transform on both sides of the given equation, Laplace transform of f dash t, which is equals to Laplace transform of sin t plus Laplace transform of f t into Laplace transform of cos t. What is Laplace transform of f dash t? From the definition, you can write down as Laplace transform of f t minus f 0. This is the Laplace transform of f dash t. Laplace transform of sin t is 1 by s square plus 1 plus Laplace transform of f t into Laplace transform of cos t, which is nothing but again s by s square plus 1. And your f 0 is 0. So, therefore, this value will be equals to 0, it is given to us. So, now if I take Laplace transform of f t common, then I will obtain s minus s by s square plus 1 into Laplace transform of f t. This is equals to 1 by s square plus 1. and on simplification you will obtain Laplace transform of f t. This is nothing but again 1 by s cube. So, that from here you can tell that your f t is again Laplace inverse of 1 by s cube, and once it is Laplace inverse of 1 by s cube, you know it that t square by 2 is the function for which Laplace transform is 1 by s cube. Therefore, for this problem f dash t equals sin t plus 0 to t f of t minus u cos u du, the solution is f t equals t square by 2. And please note that in this equation f t is coming under integral sign, you have the derivative of that f t also f dash t, but since we know the Laplace transform of the functions as well as the Laplace transform of the derivatives, using that concept we can find the value of f t as t square by 2 like this way. And so, this thing we are writing over here, Laplace transform of f dash t is this one. You are substituting the Laplace transform of cos t, f 0 is 0. So, that you obtain Laplace transform of 1 equals 1 by s cube, and once I am obtaining this, f t is Laplace transform of 1 by s cube, which is nothing but t square by 2, and value of f t is t square by 2. Let us take the next example. I want to solve 0 to t f u by t minus u to the power 1/3, which is equals to t into 1 plus t into t plus 1. So, the given integral, your function is like this. I want to solve this 0 to t f u by t minus u to the power 1/3 equals t into t plus 1. It is given to us. So, I can write it as f u 0 to t f u into t minus u to the power minus 1/3 into f u d into du, du will come over here, this is equals to t into t plus 1. And once I am writing this one, this is nothing but the convolution case. So, this will be f t convolution t to the power minus 1/3, here you have the function as minus 1/3. So, it is basically convolution of two functions f t and t to the power minus 1/3, which we can write it as 0 to t f u into t minus u to the power minus 1/3, and this is equals t into t plus 1. Now, take Laplace transform on both sides. If I take Laplace transform on both sides of the given equation, I can write down Laplace transform of t to the power minus 1/3, and this is equals to Laplace transform of t plus Laplace transform of t square. So, I can say that Laplace transform of f t into Laplace transform of t to the power minus 1/3 will be gamma minus 1/3 plus 1 divided by s to the power minus 1/3 plus 1. This is equals to Laplace transform of t is gamma 2 by s square plus this will be gamma 3 by s cube. And once I am obtaining this from here, if I make the simplification of these terms, next I can write down Laplace transform of f t into gamma 2 by 3 by s to the power 2 by 3, if I simplify this, equals 1 by s square plus 2 by s cube. And this means Laplace transform of f t, this equals, you can now write down 1 by gamma 2 by 3, this will come on this side, this gamma function, and this term will become 1 by s to the power 4 by 3, 1 by s to the power 4 by 3 plus 2 by s to the power 7 by 3. And therefore, your f t you can write down equals 1 by gamma 2 by 3 into Laplace inverse of 1 by s to the power 4 by 3 plus 2 into Laplace inverse of 1 by s to the power 7 by 3, and I know the Laplace transform of on both of them. So, that I can write it what this equals gamma 1 by gamma 2 by 3 into t to the power 4 by 3 minus 1 by gamma 4 by 3. This will be one case plus 2 into t to the power 7 by 3 is there. So, 7 by 3 minus 1 by gamma 7 by 3. And now, if I substitute, if I just make the changes from here what you are obtaining is that. So, once I am obtaining this one, then the next I can write down my f t as 1 by gamma 2 by 3 into t to the power 1 by 3 divided by 1 by 3 into gamma 1 by 3, because gamma n plus 1 is equals to n gamma n, we know it, gamma n plus 1 equals n gamma n, we are using this property, plus 2 into t to the power 4 by 3 divided by 4 by 3 into 1 by 3 into gamma 1 by 3. So, this again if you simplify, it will become 3 into t to the power 1/3 gamma 1 minus 1 by 3 into gamma 1 by 3 into 1 plus 3 by 2 into t. And this again I can write down 3 t to the power 1 by 3 into this gamma n, gamma 1 minus n equals pi by sin n pi. Using that property, this I can write down pi by sin pi by 3. I can substitute the value of pi by 3. This portion will remain as it is, 1 plus 3 by 2 into t. So, that ultimately you can write down f t equals 3 root 3 into t to the power 1/3, 3 root 3 t to the power 1/3 by 4 pi after substituting the value of sin pi by 3 into 2 plus 3 t. So, ultimately the value of f t becomes this one, 3 root 3 into t to the power 1/3 by 4 pi into 2 plus 3 t. So, as we have observed, by this way, if we have the integral equations, then always we can find out the solution of integral equations using the Laplace transform. So, if we see, this completes actually the topics on the Laplace transform. In Laplace transform, we have studied the basic properties of Laplace transform, derivative, integrations, power, division by t, these things. Then we have done the inverse Laplace transform. We have done the Laplace transform of some special function like Dirac delta function, Error function, the Bessel function like this. Then we have done the convolution, and using convolution how we can find out the solution of various equations. And at the end, towards the end, we have seen the use of Laplace transform in solution of ordinary differential equations with constant coefficients, with variable coefficients, also solution of simultaneous ordinary differential equations using Laplace transform, and today's topics we have covered solution of integral equations using the Laplace transform. In the next lecture, we will start with the Fourier series, and then we will go to the other transform, that is Fourier transform. Thank you.